Okay, this is a beam, and both ends are hinged. Okay, not roller, hinge. Both are hinged. So during if I put the constant distributed loading Q0, so once it deforms, it will deform like this, right? This length is longer than original length, so that means the actual deformation occur. So have some stretching, okay? That will create some actual forces, okay? Yeah. And this original length is L. Okay. Oh, so note here. Note. It is a hinge. Okay, hinge. Okay. No. Then my governing equation is the dw dx equals minus n0 over ei, and dw dx squared equal to q0 over ei. So this is a constant here, right? So my governing equation, this one. My homogeneous solution I already get is A hypersine lambda x plus B hypercosine lambda x plus cx plus d. Okay? Be careful. A lot of students, they directly put the boundary condition here to determine ABCD. Can we? No. You have to put the boundary condition after you got a particular solution. The boundary condition is for the total solution, not for the homogeneous solution. Okay? Yeah. So we have to find the particular solution. So the way to get a particular solution, we have to try the form and the comparison coefficient, but here is easy. You can get it by observation. That will be minus q0 over n0 times half x squared. Because this term, if you derive w with twice, this half will become constant. Okay? And that will be equal to the coefficient. And after second derivative, the first derivative certainly will be 0. So this is by observation. Okay? By observation. It's my particular solution. Right? So after you got this, my total solution will be homogeneous solution plus particular solution will be A hypersine lambda x plus B hypercosine lambda x plus Cx plus D plus particular solution is minus Q0 over N0 half x squared. Okay? Yeah. Okay. Then we put the boundary condition. Boundary condition, we have the W as 0 equal to 0, and the moment minus EI, double prime at 0 equal to 0. And the diffraction at L equal to 0 and minus EI, moment at L equal to 0. So we have 4 boundary conditions. We can determine the A, B, C, D. There's 4 coefficients. Okay? And yeah. Okay, so I don't I don't solve it. You can see my notes, right? And we can get a solution as okay. The W equal to A is Q0 over N0 lambda square 1 minus hypercosine lambda L over sin lambda L and hypersine lambda X plus the B is equal to Q0 over N0 lambda square hypercosine lambda X plus C is Q0L over N0 lambda square. Q0 N0. Q0L over N0 square X. Okay, minus Q0 N0 lambda square minus N0 Q0 half X squared. Okay. This is D. So this is a total solution. Yeah. Or we can rearrange it. Okay, or we can rearrange it as Q0 N0 lambda square hypersine lambda L and hypersine lambda X plus hypersine lambda L minus lambda X. Okay. Yeah, here we have done some combination, yeah. And plus Q0 over 2N0 X L minus X minus Q0 over N0 lambda square. So this is another form. Okay. But anyway, it can be further combined by divide this W with normalized by a Q0L square over N0, and it will become. Finally, it will be equal to 1 over lambda L square hypercosine lambda L over 2 minus 1 plus 2x over L over hypercosine lambda L over 2 plus half x over L 1 minus x over L. All right? This just to cover this x and L. You can see this is normalized. This is non-dimension. So this part is also non-dimension. Okay. Yeah. So this is a non-dimension non-dimensional equation. Okay. I think in the classical mechanics theory, if any paper, if you can generate a lot of this kind of non-dimension curve, that'll be a good paper. Okay, so because non-dimension you can for any case. Okay, they should have this kind of phenomenon. Yeah. Okay, so this diffraction curve, and let me see. Okay. Okay, so all right, so this is my solution, but n0, how much? We haven't determined yet, right? We just know the constant force n0, but for this Q loading, how much n0 is?
稍等一下。
Wow. Okay. So let's determine this n0. This is very important. You didn't before. Find n0 for this actual stretching force. Recall, my n0 is equal to sigma x times a is equal to EA and partial u, partial x plus half dw dx square. Okay. Then, or n0 minus, okay, n0 over EA minus half dw dx square is equal to partial u, partial x, right? I divide by EA, and I move this term here, so only left this term. Yeah. And yeah, and u, actually this is du dx, right? Because u is a function of x, so single variable. So du dx equal to n0 over EA minus half dw dx square, right? Then I time the dx, then I integrate both sides. Okay? And this will be equal to du. So integration of du is equal to u, and at n, 0 and L. Right? So here I have, and this is dx from 0 to L. Okay. So we have We have a U.